Am I audible?
Yes, ma'am.
Okay, thank you. So, very good afternoon, everyone. Today, before starting with today's class, that is on object detection, I would like to go through some concepts of classification, and then I will take the object detection. What we mean by classification? Classification is nothing but given an image, we want to see what type of objects that exist, right? So I need to classify the different types of objects, right? So basically, we do perform some set of problems. We do take some set of problems, like it can be a binary classification or multi-class classification, right? In case of binary classification, whether a particular, suppose I want to classify the given set of images, I would like to my model to give the output in terms of which type of input I am passing, right? I'm providing to the model, whether I'm providing the input which comprises of input which has a dog image in it or a cat image in it. So my model should predict, should give the output as, yes, this particular image belongs to dog image and this particular image belongs to cat image. So if I'm able to classify into two different classes, then we generally say it as an binary class classification problem. But in general, if you see, we have to deal with multiple classes, right? So we have to deal with multiple set of classes, right? In real-time problems. They may be like, I just want to go for classifying all set of, all set of objects that I wish to list. For example, I wish to have multi-class classification problem on a digit recognition, right? So whether a particular image comprises of zeros or 1, 2. So I say that whenever we discuss about digit classification, then I can say that yes, this particular example belongs to multi-class classification, because we are not dealing with two classes. In fact, we are going to deal with multiple classes, and those classes can be categorized as 0 to 9. Fine. So with respect to this, in continuation with object classification problem can be considered as object detection problem if I'm able to have the given an image, what object present, and I also try to localize where exactly my object that is present, right? So in general, given the input image, then what I exactly wish to perform here is where exactly my object is, and I just want to localize this particular object in the given entire image, right? So if any problem which is able to tell what type of object that does exist in the given image along with the location, okay, localization, where exactly that particular object lies. So if I consider this particular problem, then we say here as object detection problem. So object detection comprises of classification as well as localization, right? So what exactly I want my model to predict, right? I'll be providing the input image to my model, and my model should give me the image class probability plus set of bounding box parameters, right? So in the previous slide, I said with the help of red bounding box around the image, around the object, I have drawn the bounding box. So in the same way, what I wish my model to provide the output, it should provide the output in terms of class probabilities as well as bounding box parameters. So we say X, Y, H, and W. Here B is referring just to indicate that we are giving the parameters in terms of bounding box. And here 4 parameters, 4 bounding parameters we are providing with respect to object, right? So let us see what are those. X and Y are basically the center position of the object, whereas H and W here are indicating the height and width of the object, right? And for example, let us say I'm going to perform object detection where my problem comprises of 2 classes, right? So in that particular case, my output, or I can say I can prepare the target output something like this, where the first parameter value is nothing but 1. That means there exists some object, right? And what are Bx, By, Bh, and Bw? These are the bounding box parameters, center position X and Y, height and width of the bounding box, right? And here 1 is representing which particular class it lies, right? As we are taking 2 class problems, so whether these parameters, bounding box parameters, are associated with class 1 or class 2. Here with this particular example, it is very much clear that all these bounding box parameters, whatever value that it will have will be with respect to class 1. And here 0 is indicating that this particular class 2 object doesn't exist in this particular example. And what exactly before YOLO model, object detection, with this particular with this brief introduction, I hope the problem is clear to you. Object detection here is we want to see whether a particular image comprises of our object of interest, plus if it exists, then I would like to know where it exists, right? With that, in past there are many algorithms which have been which are being researched out, and one of the important algorithm, we say it as a sliding window algorithm, where the given an image, we do take a box and we do iterate over the entire entire region of the image, from left to right and top to bottom. We do have
Excuse me, ma'am.
Yes.
Ma'am, the slides are not getting updated. Like we are stuck on first slide of the PowerPoint presentation.
Is it? At least I'm able to see.
Oh, maybe there's a problem. Yeah, ma'am. Now it's visible. 1 BX, BY, BH.
Now?
Yes, ma'am.
Is it? I have moved to the next slide. That is YOLO
slide
model.
4. No, this is slide 4. We are in output slide. We are able to see.
I don't know what's the problem with this. Okay. Are you able to see the YOLO model now?
No, ma'am.
Okay. Now you should be.
Yeah, ma'am. Now a YOLO model is there.
Okay. Then there is some problem with respect to full screen. Okay, let me go through in the same way, right? So before this YOLO model, YOLO is nothing but the name of the model. Here it is, you look only once. So before this, we have certain other algorithms like RCNN, where in that particular algorithm, we do go for looking at the entire image. Okay, we take an image as an input, and we try to find, or we try to generate number of bounding boxes of the image, okay, of the entire image. And once we do generate the bounding boxes, then what exactly we do is we do try to find, with respect to each bounding box, we do take each bounding box and we do check whether whether an object exists in that particular bounding box or not. So this is a two-phase process. First of all, we are generating the bounding boxes, and later on we are trying to check whether the whether bounding box has some object in that or not. That is classification we are doing later on. In this, what's the problem is, definitely it will it is a slower process, as we are doing the model itself is complex, because we are generating the bounding boxes, and then later we are going for what do you say, classifying each of the object, whether object exists in the generated bounding box or not, right? So, and apart from this, we will also do some kind of post processing. In post processing, what are we doing? We are taking each object, and later on we are saying, we each bounding box, and we are saying we are checking, is there any bounding box which are duplicate. Duplicate here is nothing but, suppose we do have single object in the entire image, and somehow we have generated two different bounding boxes, and those two bounding boxes are intending for the same object. That means two different bounding boxes have been generated for the single object. So here is a duplicacy that exists. So what we need to do is, we need to check which one is more appropriate or accurate, and I need to remove the duplicated one, or I need to remove the other one, right? I need to keep single bounding box, because that particular box will comprises the entire object, right? Now, instead of two-phase process, we do go for a single phase process. That is, with the help of YOLO only once model, we are able to follow the single phase. In a single phase itself, I'm able to generate the prediction, the bounding boxes, as well as I'm able to generate the class probabilities, right? So what happens, given this particular input image, we do generate the different bounding boxes, right? So we can see here there are three different images that this particular image comprises of. One is one object is of dog, the other object is cycle, and the third object you can see over here, which is nothing but a car. So at the end, what I want to do is, I just want to predict, or my model should predict three different objects that exist, and along with that, along with the class label that dog, cycle, and car exist, I also want to my model also should provide the bounding box parameters for this particular object, for second object, as well as for third object. It should be able to generate. So basically, you look only once algorithm, it basically does this particular process in a single phase. Okay, that means it is able to generate the bounding boxes, as well as it is able to give the probability, that is confidence score, with respect to each of the bounding boxes that it has generated, right? And based on that, we will be able to get the final detections. We will see the complete algorithm, how it works. So here we take an input image. Given an input image, we do divide the entire image into number of grids, right? And afterwards, we do form the anchor boxes. What is the role of anchor box? Role of anchor box here is, suppose I do have the suppose I have single object in the given image, okay, and that particular object, we know that the shape of the object, and I can have the predictions around that particular object. Suppose I have multiple objects in the given input image. So in that case, I need to have some idea about the data type, the object type, okay, so that we can have some predefined anchor boxes, and which time we can be able to make our model to form the anchor boxes with the predefined anchor boxes, right? For example, if I want to have only two different objects are there, and I want my model to predict those two objects. So I'll see the type of objects that I want to predict, and based on which I'll be able to have the anchor boxes, okay? And these anchor boxes can be created manually, or they can be created some means of some other algorithm. For example, k-means is widely used to form the anchor boxes, right? And afterwards, we do generate the bounding boxes. Once we do generate the bounding boxes, we do go for calculating the class probabilities, and afterwards compute the confidence calculation score with respect to each of the bounding box that we are generating. And with the help of IOU, that is intersection over union, I'll be able to compute the confidence score. And once we get that, I do go for computing the class probability score as well. Okay, class probability score can be computed with the help of already computed object probability and the confidence score. Okay. That can be done over here. Calculate the class specific confidence score can be computed with the help of conditional class probability C multiplied by probability of the object probabilities, right? And once we compute this with the help of some thresholds, predefined threshold, I can look into the confidence score which is generated with respect to each bounding box, and I can discard few of the bounding boxes straight away. Suppose I say that we have generated for a given single object, we have like generated multiple bounding boxes. So in that particular case, what we need to do is we need to discard based on the class specific confidence score. Okay, so what we can do is we will see the threshold, we will set the predefined threshold. If the computed threshold is below 0.5, then we will discard those bounding boxes, we will not carry forward those bounding boxes. Okay, if it is greater than 0.5, we will keep those bounding boxes, and later on with the help of the other method, that is non-max suppression, we will be able to generate single object bounding box, right? And we will see in detail how it works. So the very first step that we go for creating the grids, creation of the grids, right? Given an input image, okay, we will divide that input image in some S cross S grid, and in this grid, each grid cell is responsible for detecting the object. Suppose that particular object lies, the midpoint of the object, if it is lying in the center of the grid, then we can say that that grid cell is responsible for saying that or detecting that particular object exists in that particular grid, right? Suppose each grid, once we divide the entire image into S cross S grid, then each grid cell will participate in the detection of the object to predict B number of bounding boxes. With respect to each object, each grid cell will produce some set of bounding boxes. So this B will be predefined value, right? B bounding boxes specifying the object location and confidence score for each of the object. Bounding box comprises of 5 predictions, okay? As I discussed earlier, those are X, Y, width and height. Bounding box X, Y, center positions of X and Y, that are X and Y, width and height of the object. And apart from that, we will also produce the box confidence score, right? And here Bx and By coordinates represent the center of the box relative to the bounds of the grid cell. And Bw and Bh coordinates indicate the width and height of the box and is predicted relative to the entire image, right? So for that sake, X and Y will never go beyond, it will be in the range of 0 to 1, whereas W and H can grow more than 1, right? The confidence score, it reflects how confident the model is that of the box which comprises an object and how accurate it is with respect to the ground truth, right? So how do we compute it? We do compute with probability of the object multiplied by intersection over union. Whether the grid cell has the object in that particular grid. So what is the probability of having the object in that grid multiplied by intersection over union? So how do I compute it? We can compute the intersection over union given this particular image, and suppose given this is the ground truth of the object and the red box is the predicted bounding box parameters. Then how do I compute the IOU? And definitely IOU can be computed with the help of as the formula itself suggests, that it is the size of the intersection over the union, right? So this particular overlapping region versus over the entire region, okay? That will give me intersection over union. Once we get intersection over union of a particular predicted bounding box that can be multiplied with a probability that object lie in the grid, then we can be able to generate the class probability as well, okay? Once we do get the individual object probability, then I can say that if there exist multiple classes in the given problem, then I should be able to iterate over the entire class objects, right? So each grid cell also predicts the conditional class probabilities, which indicates the class of the object to which it belongs. So which can be computed with probability of the class given their existent object, okay? Given this particular information, I am able to tell, yes, there exists an object and that particular object belongs to which class, right? And now the class specific confidence score is compared with a predefined threshold values to detect and classify the objects. As I said earlier, if the confidence score is less than the threshold value, the algorithm doesn't detect that particular object and that bounding box is discarded. So why we are taking the threshold? The thresholds are being considered because each individual grid cell can be able to compute B number of bounding boxes. So there might be the situation that there are more than one grid which are producing bounding boxes for a single object. So now we need to look at the grid which has the object's midpoint, okay? And that object's midpoint's grid is responsible to give or predict that yes, I have the object within my own grid, right? So for that sake, we need to have this kind of information, right? Pre-thresholding is required, right? And as multiple grids are generating multiple bounding boxes for a single, there may be the case that multiple bounding boxes are being generated for a single object. So for that sake, we need to discard the one which are not actually covering the midpoints of the object, right? So in that case, what we need to do is we need to discard the few of the unrelated bounding boxes, right? For example, given this particular image, and this particular image comprises of many more grids, and each grid is able to generate few bounding boxes. Here you can see that we are able to generate multiple bounding boxes, and we know that there exist only these three, 1, 2, and 3. These three are the strong bounding boxes that I've indicated, because they are having more confidence that yes, in that particular region the object lies, right? Midpoint of the object lies. Okay, and for that sake, the other bounding boxes can be discarded with while considered the predefined threshold, the threshold confidence threshold. If it is less than 0.6, then we are discarding those, and here we are retaining only 3. Right? In this also, let us suppose this particular object, this particular bounding box, again we need to compare the confidence score, okay, of these 3 bounding boxes. Okay, once we have these 3 bounding boxes around this particular object, then using this particular non-max suppression, what we can do is we can be able to know that only the maximum probability score will be carried forward. Okay, rest 2 will be discarded. In this particular image, the maximum probability score that is indicated by yellow region is considered and or is selected, and the rest 2 bounding boxes will get rejected. Right? So this is the process of you look only once, and there are many variants that do exist in this particular algorithms, right? So you can have a look into a different set of variants of YOLO, and even you can try implementing those, right? And apart from this, these are some of the generalized parameters with respect to the first version of YOLO. So in this, they have introduced many convolutional layers and pooling layers, and the loss they have used is sum of squared error loss. Why they have used sum of squared error loss? Because there might be situation that in this we are considering this detection problem as a regression problem, okay, prediction problem. For that sake, we are using sum of squared error loss. Okay, and activation function, different activation functions have been used. For example, leaky ReLU has been used for the intermediate and starting layers, whereas linear activation layer is used for the final layer, because we are doing the prediction, and with respect to linear activation layer we are using, right? And for rest of the layers we are going to use the leaky ReLU, right? And these are some of the basic building blocks of CNN, which has already been covered in the entire course by this time. And these are few references. If you wish, you can go through these references. They are related with YOLO and its variants only, right? So here was the short introduction about the object detection. What we can do is you can, apart from the course content that we are covering, you can go through this particular topic, as it has many emerging wide applications with respect to object detection, right? Okay, there is one query related with a difference between YOLO and RCNN. Here in this, we are doing in RCNN, we are first of all generating the bounding boxes, and later on we are performing the image classification. We are applying the image classification on top of bounding boxes. Whereas in this particular YOLO, we are doing both the things parallelly, right? That is why we say YOLO is much faster than RCNN. Any query, you can post it. Okay, with this, I'll end up today's session. Thank you. Thank you for joining us.
Thank you, ma'am.